Okay, in this video I'm going to be talking about some numerical ways where we're going to start looking at quantitatively predicting what's going to be happening with the concentrations of reactants and products in equilibrium. We're not going to go that far in this initial video. We're just going to get some of the background here. So the way we do it is we use something called the equilibrium constant, or sometimes called the equilibrium equation. The equilibrium constant is represented by a capital K, and it has the concentration of the products over the concentration of the reactants. More specifically, we take the coefficient of a species, so the species V, for example, here has the coefficient A, and we use that as the exponent in the equilibrium constant. W has the coefficient B, those are both of my reactants, and I would put that over the concentration of X with the coefficient C, and the concentration of my species Y with the coefficient D. So we put products over reactants, we use their coefficients as their exponents, and we're looking at concentrations here. An important side note regarding the equilibrium equation or constant is that we do not include any particle that has a fixed concentration. That means we do not include liquids or solids. We instead only include gases and aqueous things, or things that are in solution. We don't include these because they're constant, and as a result they just set out as some sort of constant number sitting here, and so we just assume that all of those things get lumped in with this K over here because they don't change, they're not interesting, and don't need to be included in the equation. Okay, so here's 4 reactions, and we're going to write out the equilibrium constant for these 4 reactions. Note for this top reaction that all of these species are gases. I included it for the other ones, but I forgot for this one. So K for the first reaction would have the products over the reactants. So my products here would be ammonia. We're going to assume ammonia gas here. And that's going to be over nitrogen gas, the one reactant. It has a coefficient of 1, so we don't bother putting a 1 in there. And hydrogen gas. And the coefficient of 3 becomes an exponent of 3 in the K expression. Looking at the acid-base reaction for the weak acid hydrofluoric acid, we would have our aqueous product, HF, on the bottom here. We would have our hydronium, which is a dissolved polyatomic, and our fluorine ion. Sorry, those should be inside. And because the coefficients on everybody in this equation are 1, all of these exponents are 1, so I don't have to put any of them in. But what's important about this is note that I do not include H2O because it is a liquid and as a result has a constant concentration. And so it's not interesting as far as the equation is concerned. So H3O, F, HF. Next, we're going to look at the disassociation of lead chloride. So here I'm going to have my products over my reactants. So my products are lead, or the lead ion. He has no coefficient, or he has a coefficient of 1, so I don't include it. Chlorine ion with a coefficient of 2. And here, I don't have to put this over anything. I mean, I can go like this over 1, because the salt, lead chloride as a solid, has a constant concentration, and so we don't include solids. So this is just this equilibrium statement here. Next here, we have a single displacement reaction where magnesium is being displaced out of a solution in favor of lithium. Here, I do not include my 2 solid products, so this would simply be lithium chloride with a coefficient of 2 and magnesium chloride with a exponent of 1, so we don't bother putting it in. So that's how we can take chemical systems and get our equilibrium constant with them. We're going to spend a lot of time discussing how to use this equation then to predict those concentrations at different points in the equilibrium. But we're not there yet, so for now we're just really practicing on how to make the equilibrium equation or how to write the statement for the equilibrium constant.